Hello everyone, myself Hiren Patel, associated with LJ Institute of Engineering and Technology. So in this current video lecture series, we are studying subject of Physics Group 1. So in last video, we have started the first chapter, that is superconductivity. So in previous video, we have discussed about what is superconductor, how it discovered by a scientist Ohms, and also we have learned few properties of superconductors. So that properties are electrical resistance, isotopic effect, critical magnetic field, critical current density, and persistent current. So, in this video, we are covering the topics such as Miessner effect and important factors that define that superconducting state. So, Miessner effect is the last property of superconductor. So, let's start with the first topic of today's session, that is Miessner effect. So, the complete expulsion of all magnetic field by a superconducting material is known as Miessner effect. In this process, the development of surface current results in the development of magnetization in the superconducting material. We know that whenever current flowing through any conductor, or we can say that superconductor, then magnetic field produced around it. Now, due to that developed magnetization and that applied magnetic field, both are in equal magnitude but in opposite direction. So they cancel each other everywhere inside the material. So we can say that at below critical temperature, superconductor behaves as a diamagnetic substance. We know that there are different types of magnetic materials that are diamagnetic, paramagnetic, and ferromagnetic. We know that ferromagnetic materials are permanent magnet, but that diamagnetic material that doesn't allow any external magnetic field penetrate through it. So again, I revise that important statement. When we apply a current flowing through the superconductor, it develops magnetization within that superconducting material. Here, both that magnetization, first is developed magnetization and second is external applied magnetic field, that both are in equal magnitude and opposite in direction. So they cancel each other everywhere inside the material. That property is nothing but the diamagnetic property. So we can say that below critical temperature, superconductor behaves as a diamagnetic substance. Now, you can see in the figure, here, there are two cases. You can see in the figure, when temperature is greater than critical temperature, or when the magnetic field is greater than the critical magnetic field. At that time, we can say that materials remains in normal state. So here, in normal state, you can see in the figure that magnetic field penetrate through the material. At that time, we can say that B is not equal to 0. B stands for magnetic flux density. Magnetic flux density is not equal to 0. It means that it allows the external magnetic field penetrate through it. So, at a normal state, or we can say that at a temperature greater than critical temperature and at magnetic field which is greater than the critical magnetic field, at that time external magnetic field penetrate through the superconductor. Now let's discuss second case. You can see in the figure, that is superconductivity state. So it is obvious that at superconductivity state the temperature is less than the critical temperature and the magnetic field is less than the critical magnetic field. We know that critical magnetic field is a minimum magnetic field that is required to destroy that superconductive state. So here in that state, at the superconductivity state, you can see in the figure the external magnetic field cannot penetrate through the material. At that time we can say that B is equals to 0. It means that magnetic flux density equals to 0. So if any material which doesn't allow that magnetic field penetrate through it, that property is also known as diamagnetic property. So in Miessner effect we can say that complete expulsion of magnetic field penetrate through the material is known as Miessner effect. So you can see in the figure that at below critical temperature the material in superconductivity state cannot allow the external magnetic field lines penetrate through it. Now let's discuss that magnetic susceptibility of that superconductor is -1, which exhibits perfect diamagnetism. So now see in the slide that this is the basic equation of magnetic flux density, that is B equals to mu0 bracket m plus h, where mu0 stands for permeability of free space, capital M stands for intensity of magnetization, and H stands for applied magnetic field. Here we know that permeability is the property of that material which allows the production of magnetic flux through it. So this is the basic equation. B is equals to mu0 bracket m plus h. Now we have discussed that at superconducting state that B is equals to 0. It means that magnetic flux density equals to 0. So if we replace that B equal to 0 in above equation, we have the another equation as mu0 bracket m plus h equals to 0. But we know that mu0 is nothing but the permeability of free space. So obviously that mu0 doesn't become 0. So here we can say that m plus h is equals to 0. So m is equals to minus h, and the ratio of m to h, it means that the ratio of intensity of magnetization and applied magnetic field is nothing but it is known as magnetic susceptibility, and that is xm. So if we replace xm equals to capital M by capital H in the above equation, then we have xm equals to -1, where xm stands for magnetic susceptibility. So we can say that from that derivation that superconductor exhibits negative susceptibility. Now let's discuss that important factors that define superconducting state. So here you can see in the figure the superconducting state is defined by three very important factors. First one is critical temperature, second one is critical magnetic field, and last one is critical current density. So now we know that a temperature at which the superconductor exhibits zero resistance, that temperature is critical temperature. Next, the minimum magnetic field required to destroy that superconducting state is critical magnetic field Hc. So we can say that if H greater than Hc, then material comes into the normal state. And last is critical current. So that maximum current that can be permitted through the superconductor without losing its superconducting property, that is known as critical current, or we can say that critical current density. So each of these parameters is very dependent on the other two properties present. So here, to sustain the superconducting state in a material, it is required to have the both current density and magnetic field as well as the temperature to remain below their critical temperature. So the highest values for Hc and Gc occurs at 0 Kelvin, while the highest value for critical temperature occurs when capital H and capital J are 0. It means we can say that highest value of critical temperature occurs when magnetic field and that critical current density becomes 0. So that's it for today's session. Now in next video we will learn the types of superconductor, that are type 1, type 2, hard superconductor, soft superconductor, as well as high temperature superconductor and lower temperature superconductor. And we will also discuss the numericals based on that properties of superconductor. So that's it for today's session. Thanks for watching.